So energy is what we call a scalar. A scalar is a quantity with a magnitude but no direction. So energy can be positive or negative, but we can't say that the energy is 20 joules south. That makes absolutely no sense because energy does not have a direction. Some other examples of scalar quantities are time and speed. So speed can be calculated using the distance over the time. And if you're ever asked to calculate the speed, then you do not need to give a direction. Velocity, on the other hand, is very similar to speed, except that it's what we call a vector quantity. A vector quantity is something which has a magnitude and a direction. So if you're ever asked to calculate the velocity of an object, you need to calculate how fast it's going, but also state which direction it's going in. So other vector quantities are acceleration and displacement. So displacement is like the distance, except that distance is a scalar, so it doesn't have a direction, and displacement is a vector, so it does have a direction. Now, often when we're dealing with vector quantities, it's useful to convert them into components. So if we're considering a vector which is going in the north, south, east, west type directions, it would be useful to work out how much of that vector is in the north direction and how much is in the east direction. If we're considering a vector which is vertical and horizontal, so for example if we throw a ball, then it's useful to convert it into components vertically and horizontally. So in order to convert a vector into its components, you'll need to be able to deal with the trigonometry of right angle triangles. So if you've forgotten this, it may be a good idea to revise it. I've placed a link to some revision material below this lecture. So if you have forgotten trigonometry of right angle triangles, make sure that you revise that quickly. So let's have a look at a couple of examples now. So the question is, a car travels 60 kilometers in 1 hour. It ends up northeast of its starting position. Part A, calculate the average velocity of the car over this interval of time. B, how far north of its starting position is it? And C, how far east of its starting position is it? So to answer this question, it's a good idea to start by drawing a diagram. So here's our diagram. The car ends up 60 kilometers northeast of its starting position. So it ends up here, and this is a distance of 60 kilometers. This is an angle of 45 degrees as it's northeast. So in part A, we're asked to calculate the average velocity. So we know that the velocity is equal to the displacement over the time. So it's travelled 60 kilometers or 60,000 meters in 1 hour. So that's in 60 minutes and 60 seconds. And so these 60s cancel out. We end up with 1,000 up there, and that is equal to 16.67 meters per second. Now this is its average speed, but it's asked us for the average velocity, so we should give a direction for this, and the direction is northeast. Part B wants us to find out how far north of its starting position is it. So we need to find out this height here. So let's call this y. So we know the size of our hypotenuse and we know y. So if we use SOHCAHTOA, we have the hypotenuse and the angle, the side which is opposite the angle. So we're going to have to use sine. So we know that sine of theta is equal to opposite over hypotenuse. So substituting in, we've got sine of 45 is equal to the opposite, which we've called y, which is what we're trying to find over the hypotenuse, which is 60 kilometers. So that tells us that y is equal to 60 kilometers times sine 45. Solving this on the calculator, we end up with 42 kilometers. And it has travelled north, so it ends up 42 kilometers north of its starting position. Now in part C, we need to find out how far east. So we need to find out this distance here. Let's call that distance x. So in this case, x is the adjacent, and we know the hypotenuse. So we'll use cos. So we know that cos theta is equal to the adjacent over the hypotenuse, which tells us that cos of 45 is equal to x over 60 kilometers. And so this tells us that x, just rearranging this, is equal to 60 kilometers times cos of 45. And solving that on the calculator, we get 42 kilometers east again. So we've answered that question now. Let's have a look at another example. So this time we're told a car travels with a velocity of 20 meters per second in a direction 30 degrees west of north. If it travels for 30 minutes, A, what total distance has it travelled? B, how far north of its starting position is it? And C, how far west of its starting position is it? So we're best off to start by drawing a diagram again. So in this case, it's travelled 30 degrees west of north. So it's travelled in this direction, and there's 30 degrees there between north and west. And we're asked, what total distance has it travelled? Well, we know that speed is equal to distance over time, which tells us that distance is equal to speed times the time. So this is part A, and so the speed is 20 meters per second, and the time, we need to put the time in seconds, so we've got 30 minutes, and so that's 30 times 60 seconds. So solving this on the calculator, we end up with 36,000 meters, which is equal to 36 kilometers. So this distance here is 36 kilometers. Let's just add it to our diagram. Now part B says how far north of its starting position is it? Okay, so we can break this vector into components. We've got a westerly component there and a northerly component there. Let's call the northerly component y and the westerly direction component x. And once again, we'll need to use trigonometry, so let's use SOHCAHTOA. Okay, so first of all, we need to find out this northerly component. Now, this is adjacent to this angle because it's right next to that angle, and we also know the hypotenuse. So we'll need to use cos. So we know that cos of theta is equal to adjacent over hypotenuse. So substituting in, we've got cos of 30, is equal to the adjacent, which we've called y, over the hypotenuse, which is 36 kilometers. So that tells us, rearranging, y is equal to 36 kilometers times cos of 30. And solving that on your calculator, you get 31 kilometers. So part C says how far west of its starting position is it. So we need to work out what this x is. So to work out x is opposite the angle that we know, and we also know the hypotenuse. So we'll be using SOH. So we've got sine theta is equal to opposite over hypotenuse. So this tells us that sine of 30 is equal to opposite, which is our x, over 36 kilometres. And so x is equal to 36 kilometres times sine of 30. So solving that on the calculator, we end up with 18 kilometres. So as we mentioned briefly, distance is a scalar and displacement is a vector. So whenever you're asked to calculate the displacement of an object, you need to include its direction. When you're calculating the distance that an object's travelled, you can ignore that direction. So let's have a look at an example doing this, because this shows you some important techniques in physics, such as adding vectors head to tail and using these to calculate the resultant. Okay, so the question is, a person walks 10 metres north, then 5 metres west, then 5 metres south. Part A, calculate the total distance they have travelled. Part B, calculate their displacement from their starting position. And then part C, comment on the relationship between distance and displacement. So to answer this question, we're best off to start by drawing a diagram again. That is often a very good way to start a physics question. So let's just identify our directions. We've got north, south, east, and west. Now what we're actually going to draw is what's called a vector diagram. We're going to use arrows to represent each of these quantities. So 10 metres north, we'll represent that with this arrow here. So an arrow showing that the person's walking north. Next, the person walks 5 metres west. So we draw an arrow which is half as long as this first arrow, and it's pointing towards the west. And notice how we've drawn the arrows together. This is what's called the head of this arrow, because it's got the arrow point. This other end is the tail. So we joined the tail of our second vector to the head of the first vector. So we say when we add vectors, which is what we're doing here, we draw them head to tail, and that's what we mean by that expression. So next we draw the 5 metres south vector. So that's going to have the same length as this vector, but be going in the south direction. And so we draw the tail of this vector at the head of the 5 metres west vector, and this is our 5 metres south vector. So this is what the vector diagram looks like. Now part A is relatively easy. Calculate the total distance that they've travelled. If we want to get the total distance, we just add each of the individual distances together, because distance does not include a direction. So 10 metres north and 5 metres south do not cancel each other out. So total distance is equal to 10 plus 5 plus 5, which is equal to 20 metres. Now part B, we need to calculate their displacement from their starting position. Well, on this diagram, here's their starting position and here's where they end up. So the total displacement is from here to here. So we can represent that by an arrow. Now I like to represent resultant vectors with a double arrowhead. You don't have to, but I find this useful to identify the resultant vector. So when we sum all of these vectors together, this is our resultant vector. So what we need to do now is work out the length of this vector. So to do this, we're actually going to have to use a little bit of geometry. That's a right angle triangle there. Now if you go 10 metres north and then 5 metres south, in total you've travelled 5 metres north. So we know that this length here is 5 metres. And we also know that they've travelled 5 metres west. So you can see that this is an isosceles triangle, and it's also a right angle triangle, so a right angle isosceles triangle, which looks like this: 5 meters, 5 meters. Since it's right angle, that's 90 degrees. So isosceles, so these two angles in here must both be 45 degrees. To work out the length of this side, what we can use is use Pythagoras' theorem. So let's let this have length L. So the length squared is equal to 5 squared plus 5 squared. So that's 25 plus 25, which is equal to 50. And so the length is equal to the square root of 50, which when we solve that on the calculator, we end up with 7.07 meters. Let's put that as 7.1 meters. These were only to one significant figure, so we could just put as 7 meters if we wanted. And then what we need to do is, because we're asked for a displacement, we also need to give a direction. So this is north, this is west, and that's 45 degrees. So the direction in this case is northwest. Now part C, comment on the relationship between distance and displacement. Well, you can see that the distance is always going to be larger than or equal to the displacement. So distance is always greater than So if a person walked 5 meters north, then 5 meters south, they have traveled a distance of 10 meters, but their displacement, for example, would be 0.